Water should not exist, not as a liquid, not on this planet, not at the temperatures we live in. By the neat patterns of chemistry, the water in your glass should be an invisible gas drifting away into the atmosphere. The oceans should be a memory. The clouds should be impossible. You should not exist. I should not exist. And yet, here we are. Now do a second experiment. Put an ice cube in that glass. It floats. For almost every substance on Earth, the solid form is denser than the liquid. When matter freezes, its molecules slow down and pack closer. The solid sinks. Water refuses. So today I want to do what I have always loved to do. Take a thing you think you understand and press on it until it becomes strange. Because water is not just a liquid, it is quietly radical. Not radical like uranium, loud and violent and dramatic. Radical like a monk, patient, ordinary to look at, and yet in complete defiance of the rules. And the defiance has a single cause, a peculiar invisible web of hydrogen bonds that makes water behave unlike almost anything else. When I was a young man in Bern, I used to sit beside the river and watch it, sometimes for hours. My colleagues would have called it laziness. My boss at the patent office would have agreed, if he had known. But I was doing the only thing I have ever been truly good at. I was asking a question that looked too simple to be worth asking. What is that really? Not, what is it made of? I knew it was water. I mean, what is the thing beneath the surface of the surface, that makes water move like that, catch the light like that, carve the world like that? I never stopped asking. Let us begin with the most famous rebellion. In a well-behaved liquid, winter should be a massacre. Imagine a lake as the air turns cold. The surface water cools first. In most liquids, colder water becomes denser, so it sinks. Warmer water rises, cools, sinks again. The lake mixes like a slow pot on a stove until the entire body reaches the freezing point. Then ice forms at the top. Now in a normal substance, that ice would be denser than the liquid beneath it, so it would sink. More ice would form, sink, pile up, and the lake would freeze from the bottom upward. Everything living in it would be locked in solid ice. Fish, plants, microscopic life, dead. And it would not stop with one winter. Ice is bright. It reflects sunlight back into space instead of absorbing it. More ice would mean a colder planet. A colder planet means more ice, a feedback loop, the kind of loop that ends in silence. Lakes would begin to keep frozen cores year after year. Shallow seas would follow. The planet would tip, slowly but inevitably, toward a permanent frozen stillness from which there is no easy return. But water does not behave. When water freezes, it expands. The solid is lighter. The ice stays on top, exactly where it must. And then something even more beautiful happens. Ice is a terrible conductor of heat, so the surface becomes a lid, and that lid becomes an insulating blanket. Beneath it, the lake stays liquid. It breathes under the ice. The fish survive. Spring comes, and the world continues. The fact that ice floats is not a cute curiosity. It is one of the hinges on which the history of life has swung. And water adds a second layer of protection, a subtler one. Most liquids get denser as they cool, all the way down to freezing. Water does that only until about 4 degrees Celsius. Around that point, it reaches its maximum density. Cool it further, and it expands again. So in a lake, as the surface cools from summer warmth, the colder water sinks, mixing the lake until the whole lake reaches roughly 4 degrees. But once the surface cools below 4, that colder water is no longer denser. It stays on top. The lake stops mixing. The coldest water gathers at the surface, where it can finally freeze. The deep water remains at about 4 degrees, heavy and stable, like a quiet refuge for life. This is not how a sensible liquid should behave. It is how water behaves. And I will tell you something personal. I have watched an ice cube float 10,000 times in my life. It still gives me a small chill, and not from the temperature. Because you are watching matter do something it almost never does. If I could show this to a physicist who had studied 1,000 substances but had never met water, he would not accept it. He would check the instruments, he would question the glass, he would assume the experiment was wrong. And he would be right to be suspicious. It is not permitted. Water simply does it anyway. Now you may say, Albert, fine, ice floats. Water is densest at 4 degrees. It is unusual, but surely this is just one corner case. No, water is full of rebellions. Let me show you a second one, and this one is so large that it should bother you. Water boils at 100 degrees Celsius, at ordinary atmospheric pressure. Your grandmother knew this. It feels like a permanent fact, like the speed of light. But look at oxygen's neighbors. Oxygen sits in group 16, sulfur, selenium, tellurium. Each of these forms a compound with hydrogen. Hydrogen sulfide is the gas that smells of rotten eggs. Hydrogen selenide, hydrogen telluride. And there is a clean, predictable trend among these compounds. As the molecules get heavier, their boiling points rise. More electrons, stronger attractions, higher boiling point. Hydrogen sulfide boils around -60. Hydrogen selenide around -40. Hydrogen telluride near 0, a steady climb. If you extend that trend down to the smallest member of the family, to water, you do not get +100. You get something like -70, -80, a gas. In other words, chemistry gives you a forecast, and water shows up 170 degrees away from the forecast. 170. In my line of work, when you miss by 170 degrees, you do not call it a charming quirk. You say, I have misunderstood something fundamental. And if water boiled where the trend suggests it should, there are no oceans, there is no rain, no rivers, no clouds. The surface of Earth is as dry as the surface of the moon. And there is something even more important than scenery. Chemistry needs a medium. It needs a solvent. A place where molecules can meet, collide, react, and reorganize. Without a stable liquid phase, chemistry becomes a thin, slow, brittle thing. It does not build the messy richness that life requires. We exist because water refuses to be a gas. Now let me tell you about heat, because water is unreasonable about heat in a way that governs climates, storms, and bodies. When I was sailing, which I did often and quite badly, I noticed something that bothered me in a productive way. The land heats rapidly under the sun. By midday, sand can burn your feet. Rocks can become too hot to touch. But the sea is slow. It accepts heat reluctantly, like a stubborn accountant refusing to balance his books. This is specific heat capacity. How much energy you must add to raise a substance by 1 degree. Water's specific heat is absurdly high. Compared to iron, it takes roughly 10 times as much energy per gram to warm water by the same amount. So the oceans become a giant thermal flywheel, a slow, patient battery of heat. In summer, they absorb enormous energy without overheating. In winter, they release that energy without collapsing into ice overnight. Coastal cities are mild because they live beside a reservoir that refuses to change quickly. Without water's heat capacity, the daily swing between noon and midnight would be savage. The surface of the earth would be an oven at midday and a freezer by night. And water has another heat trick, not about temperature, but about phase changes. To melt ice into water, you must pour in a surprising amount of energy without raising the temperature at all. To freeze water into ice, the water must give up that same hidden energy. This is latent heat. It means that as water freezes, it releases heat that slows further freezing. And as ice melts, it absorbs heat that slows further warming. Water resists abrupt change. Now add the third trick, evaporation. It takes an extraordinary amount of energy to turn liquid water into vapor. The heat of vaporization is high. So when sweat evaporates from your skin, it steals a large amount of heat with it. A small change of state carries away a disproportionate amount of energy. Your body is exploiting a loophole in the periodic table. Without it, warm-blooded life above a certain level of exertion becomes thermodynamically difficult, perhaps impossible. And at the scale of the planet, this same latent heat drives weather. Evaporation stores energy in water vapor. Condensation releases it again. This exchange is part of what powers storms, clouds, and the restless engine of the atmosphere. Water does not just store heat, it transports heat, it hides heat, it releases heat slowly, like a creature that does not panic. Now we go from heat to something you can see, if you look closely: surface tension. Place a steel needle very gently on water and it can float. Steel is far denser than water. It should sink immediately. Yet the surface behaves like a stretched membrane, like the skin of a drum. Small insects can stand on it. Droplets can form nearly perfect spheres. Water clings to itself with unusual insistence. That force drives one of the most elegant tricks in physics: capillary action. Put a thin glass tube into water, and the water climbs upward against gravity with no pump and no machinery. It rises because water is cohesive and because it likes to cling to surfaces. It rises because the surface molecules pull the rest of the liquid along with them. In the soil, capillaries help pull moisture upward. In porous rock, water creeps through tiny spaces. In your own body, water's tendency to stick and flow through narrow channels shapes biology in 1,000 quiet ways. And now think about a tree, a tall one, a redwood. Water must travel from the roots to the leaves, tens of meters upward. There is no heart inside a tree, no piston, no rotating wheel. What there is a column of water held together by cohesion, pulled upward through microscopic channels, and helped by evaporation from the leaves that creates tension, like a continuous, gentle suction. And here is an astonishing fact. In the xylem of a tall tree, water can be under tension, not pressure, like a stretched rope. It is being pulled upward, not pushed. If water had ordinary surface tension and ordinary cohesion, that rope would snap. Trees would be short. Forests, as we know them, would be different or absent. The land surface of Earth would be reshaped. So we have ice that floats, density that peaks at 4 degrees, boiling points that refuse trends, heat that hides in the liquid, and a surface that acts like elastic skin. Different phenomena, one personality, one cause. The cause begins with a shape. A water molecule is not a straight line. It is bent like a boomerang. Oxygen at the center, 2 hydrogens at an angle of about 104 degrees. That bend is not decoration, it is destiny. Oxygen is greedy for electrons. It pulls the shared electrons in the OH bonds toward itself. That leaves the oxygen side slightly negative, and the hydrogen ends slightly positive. The molecule has a plus side and a minus side, polarity, and polar molecules attract. The positive hydrogen of one water molecule is drawn toward the negative oxygen of its neighbor. The attraction is called a hydrogen bond. Now I must be precise. A hydrogen bond is not the same as the covalent bond inside the molecule. It is weaker, roughly an order of magnitude weaker. But it is far stronger than the ordinary intermolecular forces that hold together many other small molecules. It is strong enough to build a network. It lives in the middle. Strong enough to matter. Weak enough to break and reform constantly. And water has another gift. Each molecule can form up to 4 hydrogen bonds, 2 through its hydrogens and 2 through electron pairs on the oxygen. 4 connections, 4 hands reaching out to neighbors. So liquid water is not a crowd of independent molecules. It is a shifting network, a 3-dimensional web that is always forming, breaking, reforming. Not a rigid crystal, not a loose gas, something in between. A liquid with an internal architecture. Sometimes people imagine a liquid as chaos, molecules flying past one another like impatient pedestrians in a city. Water is not like that. Water is more like a city where everyone keeps grabbing hands, letting go, grabbing new hands, forming brief neighborhoods that dissolve and reform. The web is alive, it breathes. And from this one structure, the rebellions follow. Why is the boiling point high? Because to escape into the gas, a water molecule must tear itself free from that network. It must break multiple hydrogen bonds. That costs energy. Why does ice float? Because when water freezes, the hydrogen bonds encourage a specific geometry, a tetrahedral arrangement, a hexagonal lattice like a honeycomb. That lattice contains open space. The solid becomes more spacious than the liquid. Order creates holes. The liquid, chaotic and jumbled, can pack more tightly. So the solid is less dense and it floats. Why the density maximum at 4 degrees? Because as water cools, the molecules slow down and would normally pack closer. But the hydrogen bond network starts to favor that more open, ice-like arrangement even before freezing. 2 trends compete, pack tighter and open into a network. Around 4 degrees, the balance shifts. Why the high specific heat? Because when you add heat to water, much of the energy goes into bending and stretching and breaking hydrogen bonds, not just speeding up molecules. Temperature is mostly molecular speed. Water spends your heat budget on rearranging its web. Why the high latent heat of melting and freezing? Because you are not just changing temperature, you are reconfiguring the network, building a lattice, breaking a lattice. That is expensive. Why the surface tension? At the surface, molecules have fewer neighbors. They cannot form hydrogen bonds above the surface, so they pull inward, tightening the skin. One mechanism, many consequences. And the network does something else, something that turns water into the working fluid of life. Because water is polar, it is a powerful solvent. Put salt in water and it does not merely disappear. The crystal breaks apart. Sodium and chloride separate into ions. Each ion becomes surrounded by water molecules, like a crowd forming around a celebrity. The negative oxygen sides face the positive ions. The positive hydrogen sides face the negative ions. Water pulls charges apart and keeps them apart. This matters because chemistry is, in large part, the management of charges. Life is built from ions. Nerves signal with ions. Muscles contract with ions. Cells maintain gradients of ions across membranes like tiny batteries. A non-polar liquid cannot do this. It cannot stabilize separated charges. Water can, because its molecules are little magnets and because the hydrogen bond network gives the liquid coherence. And then there is the opposite behavior, equally important. There are molecules that water does not like: oils, fats, many non-polar compounds. Water cannot form good hydrogen bonds with them, so it does something very strange. It forces them together. Not because the oils attract each other strongly, often they do not, but because water prefers to bond with itself. It would rather keep its network intact than wrap itself around a non-polar intruder. So the non-polar molecules clump together, minimizing the surface area that touches water. This is called the hydrophobic effect, and it is one of the quiet engines of biology. It helps proteins fold into specific shapes. It helps membranes form, with oily tails hiding from water and polar heads facing it. It helps build the boundary between inside and outside that every cell needs. In other words, water does not merely host life as a background liquid. It actively shapes the architecture of life, simply by being the kind of liquid that it is. I have spent much of my life hunting for unified explanations. One principle beneath many phenomena. Gravity unified falling apples and orbiting planets. Hydrogen bonding, in its own quiet way, unifies oceans and ice cubes, sweat and storms, trees and lakes. It is a microscopic detail that writes macroscopic history. And it does not stop there. Here is a puzzle that has embarrassed confident people for centuries. Take two identical containers. Fill one with very hot water. Fill the other with lukewarm water. Put them in a freezer at the same time. Which freezes first? Common sense says the lukewarm water. It has a head start. The hot water must cool down to that temperature and only then begin the real race. And yet, sometimes, the hot water freezes first. This is the Mpemba effect, named after a Tanzanian school student, Erasto Mpemba, who noticed in the 1960s that a hot ice cream mixture could freeze faster than a cooler one. He told a teacher. He was dismissed. He told a visiting physicist. The physicist listened, tested, and published the result with him. What I admire in this story is not only the result, it is the attitude. Aristotle mentioned something like this long ago. Francis Bacon wrote about it. Descartes noted it. But none of them, as far as we know, sat down and did the careful, controlled experiments that science demands. It took a school student noticing his ice cream. Nature is not impressed by your reputation. Now, I will be honest. The Mpemba effect is real in some conditions and absent in others. It is difficult to reproduce reliably because it depends on details. Evaporation matters. Hot water can lose mass faster, leaving less to freeze. Convection matters. Hot water circulates differently as it cools, moving heat to the surface in a different pattern. Dissolved gases can matter. Impurities can matter. The container can matter. The freezer can matter. So there is no single clean explanation that works in every case. But there is a deeper possibility that is still being argued about, and it leads back to the hydrogen bond network. When you heat water, You do not merely make the molecules faster. You change the network. You break bonds, rearrange clusters, alter which local structures are common. And there is evidence, suggestive rather than settled, that water can cool back down while retaining a different internal arrangement than water that was never heated. Not mystical memory, physical history. Different starting conditions for ice crystals, different pathways through the same landscape. In other words, water may carry a faint fingerprint of where it has been. If that makes you uncomfortable, good. Comfort is not the goal of science. Clarity is. Now we step into territory that even I, in my lifetime, found unsettling: quantum physics. You know that I had a complicated relationship with quantum mechanics. I argued with it. I distrusted some of its implications. But I never denied its predictions. And when it comes to water, the predictions are astonishing. A hydrogen bond is an oxygen, a hydrogen, and another oxygen with the proton in between. That proton is light. Not as light as an electron, but still the lightest nucleus there is. And it sits in a strange landscape. Two low points, two possible homes. One closer to its own oxygen, one closer to the neighboring oxygen. In classical physics, the proton stays put. It does not have the energy to climb the barrier between the two positions. But in quantum mechanics, particles are also waves, and waves can leak. If the barrier is thin enough, there is a chance for the proton to appear on the other side without ever climbing over the top. Tunneling. For electrons, it is common. For protons, it is rarer because they are heavier, about 1800 times heavier than electrons. But the hydrogen bond is a very small world. Distances are measured in angstroms, in tenths of billions of a meter. In that world, the barrier can be thin. So, at sufficiently low temperatures, in certain kinds of ice, experiments and theories suggest that protons can tunnel. Not always, not everywhere, and not in a way that makes ice behave like fantasy, but enough to matter. And here is the part I find most beautiful. In the lattice of ice, a single proton moving alone can create a defect. It breaks local rules about how protons are arranged around each oxygen. That costs energy. So the motion that is favored is not a lone jump. It can be a coordinated motion, a kind of collective shuffle where several protons shift together so that the rules remain satisfied. In the ring structures that appear in ice, that can mean a concerted move around the ring, several protons shifting in step. Many particles acting together. And when many particles act together, strange macroscopic effects become possible. The material can respond differently to electric fields. Its dielectric behavior can change. Something quantum becomes visible to ordinary instruments. This kind of collective quantum behavior, where a material's properties depend on coordinated motion rather than isolated particles, appears in famous exotic phenomena: superconductors, superfluids, quantum magnets. And then you discover traces of it in ice, a crystal you can hold in your hand. That is what has always moved me. The universe does not keep separate books for the large and the small. It has one set of rules, playing out at every scale. The same type of strangeness can live in a crystal of ice and in the machinery of a star. Now step back and look at what we have done. We began with a glass of water and an ice cube, and we found ourselves talking about climate stability, biological cooling, the height of forests, storms, and quantum tunneling. That is what happens when you stare at the ordinary long enough. There are catalogs of water's anomalies, dozens of properties where it deviates from the behavior you would predict from similar molecules. A scientist once assembled a long list, over 70 separate quirks, 70 ways water refuses to be average. That list is not an embarrassment, it is a message. It tells you that the things we understand least are not always hidden in distant corners of the universe. Sometimes the deepest mystery is transparent. Sometimes it sits on your table. And if you pull the thread far enough, it goes deeper still. Hydrogen bonds come from polarity. Polarity comes from oxygen's electronegativity and hydrogen's lightness. Those come from the structure of atoms, and that structure is determined by the constants of nature, by the strength of the electromagnetic force, by the charge of the electron. So the fact that ice floats is, in the end, tied to the bedrock of physics. Could those constants have been different? Could life have found another solvent, another loophole? I cannot answer. Perhaps nobody can. But I can tell you what I feel when I consider it. Wonder. Not comforting wonder, unsettling wonder, the kind that keeps you awake. And I have come to believe that the capacity to be unsettled by ordinary things is not a distraction from serious thought. It is the beginning of serious thought. So the next time you drink water, do not treat it as background. Hold it in your mind for a moment. This quiet liquid stabilizes your climate. It cools your body. It builds forests. It carves rivers and shapes continents. It refuses to obey trends that would have made the earth sterile. The most familiar substance on our planet is one of the most peculiar. Water should not exist, and yet it does. And because it does, so do we. My colleagues in Bern thought watching water was a waste of time. I hope you disagree. Subscribe, and let us turn the rules of physics upside down together.